Hey guys, today we are looking at the double angle identities. So we've got the double angle for cosine. We've got three different options for that. So if you're looking, you can start with cosine of 2a is equal to cosine squared of a minus sine squared of a. So that's got cosine and sine in it. Or you can say the cosine of 2a is equal to 2 cosine squared a minus 1. That one just has cosine in it. Or you can say the cosine of 2a is equal to 1 minus 2 sine squared a, which just has sine in it. So you've got a couple different options for cosine double angle identities. Then you've got the sine of 2a is equal to 2 sine a cosine a. And then you've got the tangent of 2a is equal to 2 tangent a minus, or sorry, divided by 1 minus tangent squared a. So for example 1, we are given that the cosine of theta is 3/5. Sine of theta is less than 0. And then we need to find the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. So if we're starting with sine of 2 theta, we've only got one option, one identity there for us. So we're going to start with the sine of 2 theta equaling 2 sine theta times cosine theta. Now I know that the cosine theta is 3/5, so I can plug that in right there. I know I've got a 2 right here, but I'm missing parts. I don't know what that sine of theta is. And so that's where I'm going to have to do a little bit of extra work on the side over here and draw a triangle and use some SOHCAHTOA to figure out what that missing value is. Now I know that the cosine is 3/5, which means the cosine is a positive value. And I know that the sine is less than 0, which means the sine is a negative value. So if I draw a coordinate grid over here, I can use my all smarties take calculus and kind of narrow down what quadrant I have to be in. If cosine is positive, that's either quadrant 1 or quadrant 4. But if sine is negative, then that's got to be down here in quadrant 4. Because quadrant 1, everything's positive. So I know my theta is going to be down here. Then using SOHCAHTOA, like I said, I know cosine. So that's that ka from SOHCAHTOA. So I know my adjacent and I know my hypotenuse. My adjacent is going to be that 3. My hypotenuse is going to be that 5. And so I can use the Pythagorean theorem, a squared plus b squared equals c squared to find my missing side. Or I can recognize that this is a Pythagorean triple, 3, 4, 5. But since we're going down, it's going to be -4. Down in quadrant 4 means negative. So that means I can come over here and using the so from SOHCAHTOA, say that the sine of theta would be -4/5. And I can plug it all into my formula, my identity, and simplify it. That means that the sine of 2 theta is going to be 2 times -12/25. So the sine of 2 theta is -24/25. Now, I still need to find cosine of 2 theta and tangent of 2 theta. If I'm looking at cosine of 2 theta, remember I've got three options here. I'm going to stick with the option that uses what I was given in my problem. So since I was given cosine theta, I'm going to use this middle option here. Just in case I made a mistake in my triangle or something like that, then I at least get one of these right. So I'm going to say that my cosine of 2 theta is equal to 2 cosine squared theta minus 1. I'm going to plug in that 3/5. So cosine of 2 theta is equal to 2 times 3/5 squared minus 1. We got to square that. So I'm going to get 2 times 9/25 minus 1. 2 times 9/25 is 18/25. And I'm going to go ahead and write that 1 as 25/25. So when I subtract it, I get -7/25. So cosine of 2 theta is -7/25. And then the last one that I need to find is tangent of 2 theta. So tangent of 2 theta is the fraction. I've got 2 tangent theta over 1 minus tangent squared theta. Now, I don't know what tangent theta is, but I did over here make this triangle, and I can use my TOA from this triangle to help me figure out what that tangent theta is. So TOA is opposite over adjacent. So if I'm looking for tangent of theta, that would be opposite -4 over adjacent 3, so -4/3. And so I can plug that into my identity, plug that into my formula, and then just start simplifying it. The tangent of 2 theta is going to equal, well, 2 times -4/3 is -8/3 over 1 minus 16/9. 1 minus 16/9 is going to give me -7/9. So I have tangent of 2 theta is equal to -8/3 over -7/9. Then I can multiply top and bottom by 9 to kind of get rid of those denominators. So that means that I'm going to get tangent of 2 theta is equal to, on the top, -8/3 times 9 is going to give me 24, and -7/9 times 9 is 7, and those negatives cancel out, so 24 over 7. So there we go. You can also go the other way around. You can start with your double angle and work backwards to figure out what just the normal angle would be. So that's what we're going to do in example 2. It says find the values of the 6 trigonometric functions of theta if cosine of 2 theta is 4/5 and 90 degrees is less than theta, which is less than 180 degrees. So it gives me cosine of 2 theta, which is really nice because that's my one over here that's got 3 different options I can choose from. And if I look, the second option right here has just cosine, and the third option right here has just sine. So I can use both of those to help me figure out what the cosine of theta would be, and then the sine of theta, which will help me figure out all 6 of my trig functions. So let's start with that second one and figure out what cosine is going to be. So that means that cosine of 2 theta is going to equal 2 cosine squared theta minus 1. And I know cosine of 2 theta is 4/5, so I'm going to plug that in. 4/5 is equal to 2 cosine squared theta minus 1. And then I'm just going to solve for cosine theta. So I'm going to add 1 to both sides. 4/5 plus 1 is 9/5. And I'm going to divide by 2, which is the same thing as multiplying by 1/2, which makes it a little bit easier with that fraction over there. So that's going to give me 9/10 is equal to cosine squared theta. And then I can square root both sides. Now remember, when we square root both sides, we get a plus or minus with it. And this is where we're going to have to figure out if we're taking the positive or if we're taking the negative. And that's where this 90 degrees less than theta less than 180 degrees is going to be really helpful. Once again, we kind of need to look at our quadrants, where all smarties take calculus, and figure out where we're going to be. So if we are looking between 90 and 180 degrees, we're going to be up here in quadrant 2 with the S, which stands for sine. So since I'm looking at cosine right here, that means I've got to take the negative version. So that means that cosine of theta is going to be negative. And then I do still need to simplify it. I can take the square root of the top and the square root of the bottom separately. So the square root of 9 is 3 over the square root of 10. Now I can't leave it like that. I can't have a square root in the denominator. So I'm going to multiply top and bottom times the square root of 10. So for cosine of theta, my final answer would be -3 square root of 10 over 10. And if I know what cosine is, that means I also know what its reciprocal is. So remember, for cosine, the reciprocal is secant. So I can flip it, and I'm going to be really smart about what I flip, and I'm going to flip it from before I rationalize the denominator to make my life a little bit easier here. So when I do that, the secant of theta is going to be negative square root of 10 over 3. So I've got two of my trig functions now. I just need to find the other four. And like I said, our cosine of 2 theta has another option that's going to help us up here. That 1 minus 2 sine squared is going to be the next part. So I'm going to say the cosine of 2 theta is equal to 1 minus 2 sine squared of theta. I'm going to plug in that 4/5 for cosine 2 theta again, and then I'm going to go through and solve this one for sine. So I can subtract 1 from both sides. 4/5 minus 1 is negative 1/5. Then I have to divide by negative 2 or multiply by negative 1/2. So that gets me 1/10 is equal to sine squared theta. And I've got to take the square root. So sine of theta is going to equal plus or minus that square root of 1/10. We're in quadrant 2, which we already figured out from the first part. That means that S stands for sine, so we are going to take the positive version here because that S means sine is positive. So I can come over here and say the sine of theta is going to be a positive fraction. The square root of 1 is 1 over the square root of 10. I've got to rationalize the denominator again. So I end up with the sine of theta equaling the square root of 10 over 10. And now if I know sine, I also know sine's reciprocal. So when we had cosine, we knew secant. If I know sine, I know cosecant. I'm going to flip it. Once again, I'm going to be smart about what I flip. I'm going to flip it from before I rationalize the denominator. Now, if I flip that, I get the square root of 10 over 1, which is just going to be the square root of 10. So now I know 4 out of my 6 trig functions. I just need to find the last 2. Now this is where I've got to think a little bit more because now I can't just use my cosine 2 theta, my double angle identities anymore. None of those relate to the tangent or cotangent that I want to find. But I do still have some identities that could help me here. Specifically, I could use my quotient identity. I know that the tangent of theta is equal to the sine of theta over the cosine of theta. And I know sine and I know cosine. So the tangent of theta is going to equal, well, sine is the square root of 10 over 10. Cosine is the negative 3 square root of 10 over 10. And then I just need to simplify that. If I look, I can multiply top and bottom by 10 to get rid of those little denominators. So now I have that the tangent of theta is equal to the square root of 10 over negative 3 square root of 10. Those square root of 10s also cancel out. So I get that the tangent of theta is equal to negative 1/3. And if I know tangent, that means I know its reciprocal, which is cotangent. I'm just going to flip it, so I get negative 3. And there's all 6 of my trig functions. Another way these identities can be helpful is for us to rewrite certain expressions in terms of certain trig functions. So right here, for example, 3, it says write sine of 3x in terms of sine of x. Now this does say sine of 3x, and everything that we've looked at today has been a double angle, not a triple angle. So we are going to have to use some of our previous identities, some of our previous knowledge to help us out here. So what I first think of is, well, 3x is just 2x plus x, and I know a sum and difference identity. That's what we just did in our last set of notes. So instead of sine of 3x, I could write this as the sine of 2x plus x. 2x plus x is 3x. So that would be a sum identity for sine, which on my 5.4 notes, you've got that identity at the top of your notes. So remembering that identity, if this were my A and this were my B, that would be the sine of 2x cosine of x plus the cosine of 2x sine of x. And from here, I just need to fix the sine of 2x and the cosine of 2x. So remember, we're trying to get down to just x as an argument. And both of those are at the top of this set of notes. Sine of 2x, we only have one option. So I can rewrite that as 2 sine x cosine x. And that's still being multiplied by the cosine x that's next to it. Cosine of 2x, though, I have three different options. And I'm going to think about my end goal when I pick one. I'm trying to write it in terms of just sine x, which means I'm going to pick the identity that just has sine in it. I'm going to pick this bottom one that's in blue, highlighted in blue right here. The 1 minus 2 sine squared. So I can rewrite this as 1 minus 2 sine squared x, and it's also still being multiplied by the sine x. Now all of them are just x's. No more 2x or 3x, we're just x's, so let's start simplifying. Over here, if I have 2 sine x, and then I have a cosine x times a cosine x, well, cosine x times cosine x is cosine squared, so I'm going to write that as 2 sine x cosine squared x. But over here, I need to distribute. I've got 1 minus 2 sine squared x. So 1 times sine x is just sine x. And then 2 sine squared x times another sine x is going to give me minus 2 sine cubed x. Now we're almost there, but we need it in terms of sine x. And right here, I've got a cosine squared x. Now I got to figure out how I can fix that. And the first thing that always pops to my head whenever I see squares is my Pythagorean identities. And I do have a Pythagorean identity that connects sine and cosine. I've got sine squared x plus cosine squared x is equal to 1. So if I subtract my sine squared x from both sides, that gets me what I have right here, the cosine squared x. And it's going to equal 1 minus sine squared x. So I can substitute that in right there. So I'm going to have 2 sine x times 1 minus sine squared x. And then it's still plus sine x minus 2 sine cubed x. And then I just need to simplify because now everything's sines and everything's just x's. So once again, I need to distribute. So 2 sine x times 1 is just 2 sine x. 2 sine x times a negative sine squared x is minus 2 sine cubed x plus sine x minus 2 sine cubed x. And I've got some like terms I can combine. 2 sine x plus sine x is going to give me 3 sine x. And a negative 2 sine cubed x and another negative 2 sine cubed x is negative 4 sine cubed x. Now I've got sines. They're all just have x for the argument, and there we go. As simplified as it can get. Now we can also use these to help us verify some of our identities. So that's also what I have right here. Example 4, I'm going to verify my identity. Remember, when we're verifying identities, we can only work one side of that line. We're not going to move anything from one side to the other. When I'm looking at this, I would pick the left side because it's got a cotangent and then also a sine of 2x. So that gives me two things that I can kind of manipulate to move around and change and figure out to make it match that right-hand side. So if I've got a cotangent of x, I can write that as the cosine of x over the sine of x. And then that sine of 2x, that's one of the identities we just learned today. So the sine of 2x is going to be 2 sine x times cosine x. Now from here, if I'm dividing by a sine x, I can cancel that out with the sine x that I'm multiplying by. And then if I have a cosine and a cosine that I'm multiplying, I can write that as 2 cosine squared x. So I've kind of simplified it all, but I've got to see how it's going to match that right-hand side. So on the right-hand side, I'm going to notice I've got a cosine of 2x. So I'm going to come up here and look at that identity and see if any of those have a cosine squared in them, which the top two do. Now, I don't have a sine squared, which means I kind of want to look at the middle one. So let's look at that and see if we can make it work with what we have. So I have over here cosine of 2x is going to equal 2 cosine squared of x minus 1. Now we have 1 plus cosine 2x, so all I really need to do is move that over. 1 plus cosine 2x, and then it matches my 2 cosine squared x that I already have over here. So that's pretty much all that I needed to do. And we've verified our identity. These can also be super helpful with simplifying expressions. Do be careful though. So if you look at example 5, we've got cosine squared of 7x minus sine squared of 7x. This looks really, really similar to our Pythagorean identity. However, it is subtracting where our Pythagorean identity is adding. So we've got to make sure that we are being really, really careful with those signs. So if I'm looking at the subtracting cosine squared minus sine squared, that actually matches with this identity here for our double angle identity. So just make sure you're being really, really careful with your identities. If I am looking at this, that means that I would have cosine of 2a is going to equal cosine squared a minus sine squared a. So I just need to look at what my a is. If I have cosine squared of 7x and sine squared of 7x, that means my a is 7x. So when I plug that in here, I'm going to have cosine of 2 times 7x, which would be 14x. And then there's nothing else I can do to simplify that, so that would be it. For the next one, also trying to figure out what it kind of matches with. If I look up here, sine times cosine kind of sort of matches with my double angle for sine. And I say kind of sort of because you will notice this one has a 2, and down here we don't have a 2. So also remember you can manipulate these a little bit to match whatever you need. So if I have that the sine of 2a is equal to 2 sine a cosine a, I can divide by 2 to make it match. So that means that the sine of 2a all over 2 is going to match the sine of a times the cosine of a. So if I'm looking at sine of 15 degrees times cosine of 15 degrees, that means my a would be 15 degrees, and I can plug it into that kind of manipulated identity. So I would have the sine of 2 times 15 is 30 degrees all over 2. And for this one, there is more simplifying I can do. 30 degrees is a value that's on my unit circle, and the sine of 30 degrees is 1/2. So this would be 1/2 divided by 2, which is 1/4. Then we're going to kind of finish the notes with some other new identities, the product to sum identities and the sum to product identities. These are kind of less common identities. They're not used as often. So we're just going to do kind of one example of each. So remember, product is multiplying, sum is adding, or also difference here too. You could be subtracting. So for example 8, it says write 4 cosine 75 degrees sine 25 degrees as the sum or difference of two functions. So if I have cosine times sine, that's going to match with this one right here in the bottom right. If I'm looking at this though, notice that we've got a 4 in front. So we need to make sure that we keep that 4 in front and then we use our identity. And because these are kind of not as common identities, these ones you do not have to memorize. I will give you these ones on your test. So I'm going to use this part of the formula. So times 1/2, and then it's sine of a plus b. So let's say 75 is a, 25 is b. So sine of 75 degrees plus 25 degrees. And then minus sine of a minus b. So sine of 75 degrees minus 25 degrees. And then we just got to clean it up. So 4 times 1/2 is going to give me 2. And then sine of, well, 75 degrees plus 25 degrees is 100 degrees minus sine of 75 degrees minus 25 degrees is 50 degrees. And then I would just distribute the 2. So 2 sine of 100 degrees minus 2 sine of 50 degrees would be your answer there. And that would be all you could do. Sometimes, though, you will get angles that are on the unit circle, so make sure you're paying attention. For this one, though, 100 degrees and 50 degrees are not on the unit circle. And then it can go the other way around. You could have a sum or a difference that you then need to write as a product of two functions. So if I'm looking at sine of 2 theta minus sine of 4 theta, to write that one as a product, sine minus sine would match with this top right corner right here. So I'm going to plug all that in. I'm going to have the 2 and then the cosine of a plus b over 2. So let's say this is a and this is b. So 2 theta plus 4 theta over 2, and then sine of a minus b, so 2 theta minus 4 theta over 2. Well, 2 theta plus 4 theta is 6 theta over 2 would give me 3 theta, and 2 theta minus 4 theta is negative 2 theta over 2 would be the sine of negative theta. The last thing I would need to do here is I don't want that negative theta in there, so I would use my even and odd identities. Sine is an odd function, so that negative can come out. And I'm going to bring it all the way in front of that 2 up there, so I would have negative 2 cosine of 3 theta sine of theta. I want to bring it all the way to the front so it doesn't look like I have 2 cosine 3 theta then minus sine theta. The negative at the very, very front just makes it so you're not like confusing if you're multiplying by a negative sign or subtracting sign. So make sure you bring it all the way to the front, and then that's it. Great. Let me know if you have any questions on this set of notes. Make sure you get started on your My Math Lab assignment that goes with it, and you guys have a good day.